In control system theory, the Routh-Hurwitz stability criterion is a mathematical test that is necessary and sufficient condition for the stability of linear time-invariant control system. The Routh test is an efficient recursive algorithm that English mathematician Edward John Routh proposed in 1876 to determine whether all the roots of the characteristic polynomial of a linear system have negative real parts. German mathematician Adolf Hurwitz independently proposed in 1895 to arrange the coefficient of polynomial into a square matrix called the Hurwitz matrix and shows that polynomial is stable if and only if the sequence of determinants of its principal submatrices are all positive. So let us see Routh-Hurwitz stability criteria and how to find out the roots for a given characteristic equation or a transfer function. Consider general form of closed loop transfer function n of s upon a4 s to the power 4, a3 is to the power 3, a2 is to the power 2, a1 is to the power 1, and a0. This is the fourth order characteristic equation at the denominator. Input is Rs, output is C of S. For this closed loop transfer function, we have to apply Routh-Hurwitz criteria and we have to find out the stability of system. First we have to draw a root table or array. For the given equivalent closed loop transfer function, the characteristic equation is, which is denominator of transfer function. So the characteristic equation is now draw a root array. X to the power 4, x to the power 3, x to the power 2, x to the power 1, and x to the power 0. Now coefficient of S4 is A4. Put in first column A4. Now you have to skip one term, that is A3. Next term is A2. Skip one term. Next term is A0. Coefficient of S3 is A3. Skip one term, A1 and 0. Now to calculate the values of third row, you have to make the matrix of A4 and A3, A2 and A1 outside, negative sign, A4, A3, A2 and A1 divided by A3. Say this is the value B1. Now to find out second value, third row, consider matrix A4, A3, A0 and 0 divided by A3. Say this is B2. Now if you solve the given matrices, you get B1 is equal to A3 into A2 minus A1 into A4 divided by A3. Similarly, solve second matrix. B2 is equal to A0 into A3 minus 0 is equal to A0. B3 first, one column is 0. Now to find out the fourth row, we have to consider second and third row, from which we have to pick the determinant A3, B1, A1 and here B2 divided by B1. Now C2 is equal to A3 1 0 B3 divided by B1. B3 is equal to A3 B1 divided by B1. And solve the determinant. If you solve the determinant, you directly get answer 0 because B3 and above that 0 is B1, so full column is 0. Now find out the values of last row. T1 is equal to B1 C1, B2 C2, divided by C1. B2 is equal to B1 C1 B3, directly I am writing here B1 C1 0 0 divided by C1. No need to note down like matrix, you directly note down the answers. Structure of Routh array. In this way you have to represent the Routh array. Let us see how can you interpret from the Routh array. You have to observe first column first column, when you are shifting from first row to the second row or second row to the further, is there any sign change? If sign change, you can say that no roots are present, system is stable. Let us see. Stability criteria. Look at the S plane. This is the S plane. This is the left hand side plane, right hand side plane. If the roots are available in left hand side plane, system is stable. If the roots are in right hand side, the system is unstable. Verify first column of root array. If sign changes when shifting from first row to the next row, and if sign not changes. If sign changes, we can say roots or poles are present in right hand side plane, so that system is unstable. Number of roots equal to the how many times sign change. If no sign change, then roots or poles are not present in right hand side plane. All the poles are lying in the left hand side plane, so the system is stable. Let us see one numerical based on the Routh-Hurwitz criteria. Assess the stability for k is equal to 100 and k is equal to 1000. K upon s plus 2, s plus 3, s plus 4, s plus 5. Let us try to find out stability for the given numerical. First of all, find out the transfer function for k is equal to 100. Transfer function is C of S upon R of S. Now for the eliminating feedback loop, formula is G upon 1 plus Gs. By this formula, try to eliminate feedback loop, find out the transfer function. Feedback loop is negative. If you solve this, you get the final answer 100 upon to the power 4 plus 14s cube plus 71s square plus 154s plus 220. The denominator of transfer function is nothing but the characteristic equation which is required to draw a Routh array. So the characteristic equation is now draw a Routh array. S to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. Now coefficient of S4 is 1. Skip one term, that is next term is 71. Again skip one term, 220. Coefficient of S cube is 14. Skip one term, 154. Last term is 0. Now solve for a determinant. That is 14 into 71 minus 1 into 154 divided by 14. To solve this, we get answer 60. Now try to solve. Now try to find out next term. That is 14 into 220 minus 0 divided by 14. If you solve this, you get answer 220 is equal to, now next term is 0. Now try to find out next row. (14 into 220 minus 60 into 154 divided by 60. If you solve this, you get answer you get answer 102. Answer is 0. Next time is 0. Now find out the last row. 102 into 220 minus 16 into 0 divided by 102. So the answer is 220. Next term is 0. 0. This is the Routh array. Now we have to observe Routh array first column, that is 140, 60, 102 and 220. The signs of the first columns are not going to change, means all signs are positive. So the interpretation from the Routh array is no sign change in the first column. So no roots are present in left hand side. So no roots or poles present in right hand plane. So the system is stable. Let us try to find out stability for the second condition, that is k is equal to 1000. Find out transfer function C of s upon R of s. You get final answer 1000 upon s to the power 4 plus 14 s cube plus 71 s square plus 154s plus 1120. Now the characteristic equation is the denominator of transfer function. Now draw Routh array for a given characteristic equation. S to the power 4, s to the power 4, s to the power 3, s to the power 2, s to the power 1, and last row is s to the power 0. So note down coefficients of S4, skip one term, again skip one term, that is here 1120. Coefficient of S cube is 14. This is the first and second row. Now for the third row, solve matrix 14 into 71 minus 1 into 154 divided by 14. Now next element 14 into 1120 minus 1 into 0 divided by 14. Last element is 0. If you solve this, you get answer is equal to 60 for this 1120. Again proceed for the next row, that is if you proceed for the next row you get answer minus 107, 0 and 0. And for the last row 1120, 0 and 0. Now if you observe the elements in the first column, here sign is changing from positive to negative, negative to positive, means 2 times sign is changing. So the interpretation from the Routh array is in first column 2 times sign changes, so roots or poles are present in right hand side. Two roots or poles are present because 2 times sign is changing. So you can say that system is unstable. Thanks for watching this video. Watch my next video for special cases on Routh and Hurwitz criteria.